Here we are, section 4.1, general properties of aqueous solutions. In order to work forward through this section, you have to know three different terms: solute, solvent, and solution. Okay, so a solution is a homogeneous mixture of two or more substances. A solute is the substance that's present in a smaller amount, and the solvent is the substance present in a larger amount. Typically, solutes are dissolved in solvents. And then we have one more term that we need to know, which is an aqueous solution. An aqueous solution is a solute dissolved in water, and that whole solution is called an aqueous solution. And here are two more terms that you need to know: electrolyte and non-electrolyte. An electrolyte is a solute that, if it's dissolved in water, allows the water solution to conduct electricity. A non-electrolyte is a substance that, when it's dissolved in water, does not cause the water solution to conduct electricity. And now we'll do some examples. All right, so some examples of electrolytes: sodium chloride, hydrochloric acid, sulfuric acid. And in general, soluble ionic compounds are all electrolytes. Strong acids are also electrolytes. Non-electrolytes include sugar, C6H12O6, carbon dioxide, sulfur dioxide, and any molecular compound that is not an acid or a base would be a non-electrolyte. Okay, I've just added in the word strong electrolytes on the left side. You'll see it there. And the examples I've given so far are all the strong electrolytes. There is also something called a weak electrolyte, and we're going to learn about those now. Okay, weak electrolytes are electrolytes, but they only allow the aqueous solution to conduct electricity, very, very weakly. An example of this would be a weak acid, and another example would be a weak base. We're going to learn about weak acids and weak bases very soon, and you'll learn the difference between them. So for now, we know that acids are compounds that start with hydrogen in the formulas. For this class for now, all acids are going to start with hydrogen. We learned about naming them earlier. And we're going to separate all the acids into strong and weak acids. And you'll also learn about strong and weak bases, but don't worry about that just yet. Okay, so when we have ionic compounds dissolved in water, we have something happen that's called hydration. Hydration is when an ion is surrounded by water molecules in a specific manner. It turns out that water molecules have a positive and a negative side. So right here we see a water molecule, the red circle with the two white circles. So a red circle with the two white circles here, that's our water molecule. These are the H's. And the middle is an oxygen, which you can't see. We'll put a little blue here to show you the oxygen. And the oxygen side has a very slight, that's a Greek letter D for delta, and delta means very small. So the oxygen side has a very small negative charge, and the hydrogen end of a water molecule has a very, very small positive, a delta plus charge. So ions have a charge, positive or negative. The sodium ion right here has a positive charge, so the negative ends of the water molecules will be attracted to the positive sodium ion. I've got three different images here. The image on the top right that I've just put a square around is an image of sodium showing the negative water side attracted to the positive sodium ion. And on the right of the square is a chlorine. The green circle is a chlorine ion, which has a negative charge. So you'll see the positive ends of the water molecules are attracted to the negative chlorine. Down at the bottom here, I just have another image of the chlorine and the sodium showing you yet another image of hydration. Okay, another new term, chemical equilibrium. What we have learned so far is the concept of reactants making products. That's all we know, that a reaction goes to completion. When we see a single arrow, as shown here, just a single arrow, that means the reaction goes to completion, assuming that you have enough reactant and of each reactant, no limiting reactant, for the reaction to go to completion. Okay, now we have a new concept of equilibrium. In an equilibrium reaction, the reactants do form products. However, the products can also form reactants. When we have a reaction that can go in the forward or reverse direction, we put two arrows, as you see right here. One arrow pointing forward and one arrow pointing in the reverse. Now, some people in some books will show you just the top half of an arrow and the bottom half, and some books will actually show you completed arrows. Those mean the same thing, whether you have a half arrow or a whole arrow. But the key to an equilibrium reaction is that you have arrows pointing in both directions. And a reaction is considered to be at equilibrium when the reaction does go in the forward and reverse direction, but also the actual concentrations of reactants and products don't change. When those concentrations stop changing, you are at chemical equilibrium. And we'll have a whole chapter just on equilibrium a little later.